We're going to look at how to find horizontal tangent lines of a function. So first thing we need to think about is, what does that even mean? Well, if we have a horizontal line, we know that means it's going to have a slope of 0. And if we're talking about a tangent line, the way we find its slope is with a derivative. So effectively, when we're looking for a horizontal tangent line, it means we need to find when dy dx is equal to 0, or when the derivative of our function is equal to 0. So we'll start by taking the derivative of our first function, y equals x to the 4th minus 2x squared plus 1, giving us dy dx equals 4x cubed minus 4x. We'll set that equal to 0, and then just factor and solve. Factor out the 4x, leaving you with 4x times x squared minus 1 equals 0. And then you can finish factoring using a difference of squares. You get 3 different pieces. 4x times x plus 1 times x minus 1 is equal to 0. And from there, we'll just use the zero product property, separate each one into its own little equation. If 4x equals 0, that would tell us that x must be 0. If x plus 1 equals 0, x must be negative 1. And if x minus 1 equals 0, x must be 1. So we've now found the locations of the horizontal tangents. All we need to do is plug each of those 3 values back into our original equation to find the equation of the actual tangent line. Remembering that the equation of a horizontal line is always just y equals b. So if we plug in 0, y of 0 is 0 to the 4th minus 2 times 0 squared plus 1, or just 1. So x equals 0 yields the horizontal tangent line of y equals 1. Plugging in negative 1 gives us negative 1 to the 4th minus 2 times negative 1 squared plus 1. And negative 1 to the 4th is just 1 minus 2 times negative 1 squared, which is just minus 2, plus 1 gives us 0. And we'll note that if we do the same thing with x equals 1, 1 to the 4th is also 1, and 1 squared is also 1, so 1 minus 2 times 1, plus 1 yields 0 again. And so we have the same tangent line, y equals 0, coming from both x equals negative 1 and x equals positive. This question is again asking us to find the horizontal tangent lines. So again, we'll need to take a derivative. It doesn't matter what notation we use. I'll choose y prime this time. And using the power rule, that'll give us y prime is equal to x squared minus 4, which we then just need to set equal to 0. We do that, we'll factor into x plus 2x minus 2, again using a difference of squares, and find that our horizontal tangent lines occur at x equals negative 2 and x equals positive 2. We'll then evaluate our function at both of those values. Y of 2 is 1/3 of 2 cubed minus 4 times 2 plus 9. And that would be 8/3 minus 8 plus 9, or 11/3. So x equals 2 gives us y equals 11/3 as our horizontal tangent line. And plugging in negative 2, we end up with 1/3 times negative 2 cubed minus 4 times negative 2 plus 9, or negative 8/3 plus 8 plus 9. 8 and 9 is 17, which is 51/3. And if you subtract 8/3 from 51/3, you get 43/3. So our other horizontal tangent line is y equals 43/3. We'll do one more quick and easy one. Again, we're looking for the horizontal tangent line, so we'll take the derivative. F prime of x is 3x squared minus 24x plus 45. all again using the power rule. We'll set it equal to 0 and factor out the 3 to begin with, leaving us with x squared minus 8x plus 15 is equal to 0. And again, that'll just factor real nicely to x minus 3 and x minus 5. And so we'll again use the zero product property. X minus 3 will yield x equals 3, and x minus 5 gives us x equals 5 as the locations of our horizontal tangent lines. From there, again, we're just going to take each of those values and plug them into our function. So f of 3 is 3 cubed, which is 27, minus 12 times 3 squared, which is 12 times 9, plus 45 times 3, minus 10. And if we go through all of that, 27 minus 108 is negative 81. Add 3 times 45 to that. 3 times 45 is 135. And then subtract 10, you end up with 44. So we get y equals 44. Then we'll look for f of 5. F of 5 is 5 cubed, which is 125, minus 12 times 5 squared, or 12 times 25, and then plus 45 times 5, which ought to be plus 225, minus 10. Go through all of that, and looks like you end up with 40. And so our other horizontal tangent line is y equals 40. Now, most of the problems that we're going to look at are not going to be quite as easy as that one. For this one, we've clearly got some trig functions, which means it's going to be really important for you to know all the values of your trig functions for this unit. So again, the calculus steps remain the same. We're going to take a derivative, y prime, and cosine 2x can be differentiated using the chain rule. That becomes negative 2 sine 2x. And then the derivative of 2 cosine x is just minus 2 sine x. We will again set equal to 0 and solve. The first thing we'll do probably is factor out a negative 2, leaving us with negative 2 times sine 2x plus sine x is equal to 0. And then we'll notice that sine 2x can be broken down using the double angle identity. So this becomes negative 2 times 2 sine x cosine x plus sine x. And we now have a sine x that can be factored out, leaving us with negative 2 sine x times 2 cosine x plus 1 equals 0. And now we've got a multiplication of two different terms, negative 2 sine x and then 2 cosine x plus 1 that equals 0. So just set them both equal to 0. This gives us sine x equals 0, where x is either equal to 0 or pi on the interval that was given to us, half of an interval 0 to 2 pi. And then this one, 2 cosine x plus 1, when we set that equal to 0, a little rearranging gives us cosine x equals negative 1/2. And we know cosine is equal to a half at angles where the reference angle is pi over 3, and cosine is negative in the second and third quadrants. So that'll give us x equals 2 pi over 3 and x equals 4 pi over 3. And we've now found 4 locations for horizontal tangent lines, which means we just need to go in and evaluate our function at each of those x values. So at 0, we're looking at the cosine of 0, which is 1, plus 2 times the cosine of 0. Cosine of 0 again is 1, so that's 1 plus 2, or 3. So x equals 0 will yield y equals 3 as our horizontal tangent line. If we plug in pi, we end up with the cosine of 2 pi. Remember that 2 pi is effectively the same as 0. So the cosine of 2 pi or the cosine of 0 is still just 1. And then the cosine of pi is -1. So this is plus 2 times -1, which gives us -1. So pi yields for us y equals -1. For 2 pi over 3, the cosine of 2 times 2 pi over 3, that's the same as the cosine of 4 pi over 3. And we already know what the cosine of 4 pi over 3 is. We just did it over here on the right just a couple minutes ago. The cosine of 4 pi over 3 is -1/2. And then we will add to that 2 times the cosine of 2 pi over 3, which again is also -1/2. We end up with -1/2 minus 1, which is -3/2. And when we plug in 4 pi over 3, we're going to see that we're going to get the exact same value. We double 4 pi over 3 for cosine 2x. That's 8 pi over 3. 8 pi over 3 is effectively the same as 2 pi over 3 if you knock 2 pi off of it. Cosine of 2 pi over 3 is -1/2. And then 2 times the cosine of 4 pi over 3 is 2 times -1/2. And that also yields -3/2. So both of these will give us y equals -3/2 as our horizontal tangent lines. And at this point, let's just take a quick look at what this really means. So if I open up Desmos here and put in the cosine of 2x plus 2 times the cosine of x, we can see what that graph looks like. And we can see that at x equals 0, the y value is 3. And it sure looks like if I were to draw a tangent line at that local maximum there, we'd end up with a horizontal tangent line. The same thing is happening here at this local minimum of -3/2 when x is 2 pi over 3, and here for when x is 4 pi over 3. We have a local minimum, and then we have this little local maximum at pi -1. We can see that all of these horizontal tangent lines are locations of local minimums or maximums on our function. This question is asking us something slightly different. It's asking about the equations of horizontal and vertical tangent lines. And so for horizontal tangent lines, we know what to do. But for vertical tangent lines, we have to think back a little bit to when we talked about 4 reasons why a derivative might not exist. The 4 reasons why a derivative might not exist were a corner, a cusp, a vertical tangent line, or a discontinuity. And so one of those options is the thing that we are looking for right here, the vertical tangent line. So we're going to need to see when our derivative is undefined in order to figure out if we have vertical tangent lines. Now, there's going to be a few other things that we need to do as we move through to figure out why it's not a corner or a cusp or a discontinuity, but we'll worry about that as we get to it. So for now, we know that we need to find when the derivative is 0 for the horizontal tangent line and when the derivative is undefined for the vertical tangent line. So let's go ahead and take our derivative. This one requires us to use the product rule. F prime of x will be 2x times the derivative of x minus 4 to the 1/3. And x minus 4 to the 1/3 is differentiated using the chain rule. It's 1/3 of x minus 4 to the -2/3 times the derivative of x minus 4, which is just 1. And then for the second half of the product rule, it's the derivative of 2x, which is 2, times x minus 4 to the 1/3. And just looking at that equation right off the bat makes it a little difficult to see when this is equal to 0 and when this is undefined, which is why it's really important that we're able to simplify down these derivatives into singular fraction terms. So first thing we'll do is drop that x minus 4 into the denominator with the 3 from the 1/3. So 3 times x minus 4 to the positive 2/3. And then we will get ourselves a common denominator. And that common denominator is just going to be 3 times x minus 4 to the 2/3, which means we need to multiply the numerator over here also by 3 times x minus 4 to the 2/3. And when we go through doing this, we end up with 2x plus, well, in the second fraction, 2 times 3 is 6. And x minus 4 to the 1/3 and x minus 4 to the 2/3 both have the same base. So all you have to do to multiply them together is add the exponents. 1/3 or plus 2/3 is just 1. So that's 6 times x minus 4 to the first power, all over 3 times x minus 4 to the 2/3 power. And we'll simplify out that numerator a bit, giving us 2x plus 6x when we distribute, which is 8x. And then distribute that 6 to the negative 4, gives us 8x minus 24 over 3 times x minus 4 to the 2/3 power. So we've now got a nicely simplified version of our derivative. We just need to figure out when does it equal 0 and when does it become undefined. So our derivative will equal 0, any fraction equals 0, if the numerator of that fraction equals 0. So we'll say dy dx equals 0 if 8x minus 24 equals 0. Little quick algebra tells us that that's x equals 3. One thing we'll talk about just a little bit more in a minute, though, is that we need to make sure that this value doesn't also make our denominator 0. Because if we end up with a form 0 over 0, that's not going to yield either a horizontal or a vertical tangent line. I think we can really quickly see, without writing anything out, that if we plug 3 into the denominator, we don't get 0. So we are definitely going to have a horizontal tangent line at x equals 3, which means that we'll need to find what f of 3 is. F of 3 is just 2 times 3 times 3 minus 4, which is negative 1 to the 1/3 power. And that's 6 times the cube root of negative 1, or negative 6. So we have a horizontal tangent line of y equals negative 6. And it occurs at an x value of 3. To figure out when we have a vertical tangent line, we need to take this fraction and see when it's undefined. Well, a fraction is undefined if its denominator is equal to 0. So we'll say this is undefined if 3 times x minus 4 to the 2/3 power equals 0. Well, the only way for that to be 0 is if x minus 4 equals 0, which would give us x equals 4. And since the equation of any vertical line is always just x equals a, we don't really need to go back in and evaluate our function for anything, because we've already got x equals 4. And that is our vertical tangent line. And as we'll see down the road a little bit, we'll also want to make sure that doesn't make the numerator equal 0, but we know it doesn't because we found that the only thing that made the numerator equal 0 was x equals 3. If we want to take a quick look at the graph of this one, go back to Desmos for a second. And we've got 2x times x minus 4 to the 1/3 power. And as we look at that, we can see that we have a horizontal tangent line down there at 3, negative 6. And at x equals 4, happens to be the 0.40, it sure looks like this thing is turning into a vertical line, kind of vertical tangent line there at x equals 3. And it sure looks like our answers were good. So as we work our way through the problems in this unit, we're going to come across some more difficult implicitly defined equations. And we'll talk a little bit more about how to deal with those next time.